As we heard from Ashley Barnes in the previous video, hot expanding cavities turned superbubbles make up a large part of galactic structure. The prevalence of bubbles was predicted and shown in the Milky Way as far back as the 1970s. Observations of dust extinction helped reveal overlapping dusty arcs that were inferred to be bubble walls. This led to them being described as a cosmic bubble bath in 1974 by Brandon Zeiley. Then, in 1977, the well-known theory paper by McNee and Ostreicher describing the three-phase structure of the interstellar medium, or ISM for short, needed hot supernovae-driven voids to create the hot phase. In more recent times, we saw the Milky Way bubble bath in much better detail using Spitzer. This beautiful Spitzer image of the galactic plane really highlights all the small ionized bubbles created by stellar feedback. Green shows polycyclic aromatic hydrocarbons, or PAHs, fluorescing via stellar light, while red shows hot dust emission heated by stars filling the cavity. But line-of-sight observations in the Milky Way really struggle to connect the feedback to the larger scale gas structures within galaxies. With the superb resolution of JWST, 10 times sharper than Spitzer, we can unambiguously see how persistent bubbles are in nearby galaxies at 10 parsec resolution. These exquisite views really capture the bubbly nature of galaxies and the constant interaction between molecular gas and stellar feedback mechanisms such as stellar winds and supernovae. Both Spitzer and JWST really highlight bubble structures due to strong emission of PAHs at mid-infrared wavelengths. PAHs fluoresce due to stellar light, which is everywhere. But when stars recently form in young clusters, we get an increase in stellar light that helps PAHs shine more brightly. Finally, PAHs are destroyed by UV photons, which young clusters driving superbubbles have in abundance. This makes the cavities dark in PAHs, while helping circular rims shine more brightly due to the increase in stellar density locally. As a result, bubble features stand out in PAH emission. This means in just one of these galaxies, NGC 628, observed using JWST as part of the Cycle 1 PHANGS Treasury program, I was able to identify 1,694 feedback-driven bubbles. Amazingly, if we include the remaining 73 nearby galaxies that will have PHANGS JWST observations, we could find up to 300,000 more bubbles. But with the bubble sample we already have in NGC 628, we can see that stars must continue to form in the shells of bubbles, with 31% of bubbles containing a smaller bubble in its shell. Moreover, we find that the size distribution of bubbles, which is mainly controlled by the pressure balance of the bubbles with the ISM, is too shallow compared to theory. We find the tail of the distribution has a power law of minus 2.2, but theory predicts it should be minus 2.7. This can happen if small bubbles expand in the shells of larger bubbles, causing them to merge together. Therefore, with less small bubbles detected, the power law becomes shallower. This is direct statistical evidence that star formation is clustered into bubble shells. With bubbles playing such a large role controlling galactic structure, understanding how they impact star formation that is occurring in these structures will be vital to understand how feedback regulates star formation efficiencies to 1%. So to study this, I found and then characterized the molecular gas in a sample of superbubbles across 18 galaxies using ALMA CO. For more information on the ALMA PHANGS survey, you can watch the video linked in the description. Focusing on CO allows us to study the gas that can fuel future star formation, and allows us to assess the impact superbubbles have on the star-forming gas itself. To gain as much information on the evolution and the future of these regions, we focused on a subset of PHANGS galaxies that had detectable ALMA CO, had broadband HST observations in the B band at 438 nanometers and were observed with Muse VLT. This limited us to only 18 galaxies. HST allows us to study the stellar populations fueling the bubble expansion into the ISM, while Muse VLT allows us to characterize the ionized gas that fills the bubbles. We therefore detect superbubbles in the 18 galaxies if we saw a shell-like morphology in CO, along with some stellar populations inside the bubbles found using HST, as well as ionized gas emission in the shell using Muse observations. With these 18 galaxies, we find 325 superbubbles. Unlike JWST, the CO within superbubbles are hard to detect because CO is just more fragile, and so feedback driving the bubbles quickly destroys detectable CO by 10 million years. This means the bubbles do not get very big before we can no longer detect them in CO. This also means we detect less bubbles because the CO observations only have a resolution of 100 parsecs, and so many will be hard to detect by the time they reach the sizes we can probe them at this resolution. While 325 superbubbles might not seem like a lot, especially compared to the 1,694 bubbles we found using JWST in just NGC 628, before this work, the most molecular superbubbles in CO detected in a single galaxy was 4 in NGC 253, a galaxy which is 5 times closer to the Milky Way than the average galaxy in the PHANGS sample. But we find 6 bubbles in each galaxy we looked at. Since our molecular superbubble catalogue is novel work, we decided to focus on a subset that we peer-reviewed to have perfect unbroken shells. In other words, we looked at objects that were undeniably superbubbles. This resulted in studying the 88 superbubbles you see before you in a false colour rendition. The ionized gas has been illustrated with green spots, which are likely sites of recent supernova, and in blue we can see the young stellar populations that formed to create these bubbles. On average, the bubbles have radii of 130 parsecs, and because we have CO, we are also able to look at their velocity information by creating position velocity diagrams to calculate their expansion velocities. Finally, since we have HST observations of these bubbles, we can use SED modelling to determine the age of the stellar populations driving the bubbles as a proxy for the age of the bubbles. The radii, expansion velocities and ages allow us to determine the feedback mechanism powering the bubble by using a self-similar expansion model. Here we can see eta is the only unknown, and its value encodes the feedback mechanism driving the bubble. We find that eta has an average value of 1/4, which is the exact value you'd expect if the bubbles are driven by a supernova blast wave. We can see that when using a value of 1/4 when plotting the CO on this figure, HST and CO are 1-to-1. However, the go-to assumption is that bubbles are powered by a continuous injection of energy, such as winds, which is represented with eta equaling 1/2. While around 1/3 of bubbles would be consistent with eta of 1/2, the majority are not. Therefore, molecular superbubbles at 100 parsec scales are mainly powered by a supernova blast wave model. We should be cautious when using a single wind-like model to describe superbubble expansion and when calculating the energy they inject into the ISM. Since here, when calculating the feedback injection efficiency using a starburst 99 model for the stellar populations, compared to the kinetic energy of the shell over time, a wind-like model predicts that feedback injects this energy 20% efficiently. With a supernova model, we only need an injection efficiency of 10%. This is a factor of 2 difference and is important when you consider that we found 2 to 6% of all the molecular gas surveyed in these galaxies to be locked up in superbubble shells. This relatively large percentage therefore implies we could have up to 6% of molecular gas locked out of the next generation of star formation if feedback is destroying the molecular gas as the bubble expands. To see if this is the case, we look at how the amount of gas in the shell changes over time, compared to the stars in the centre. If we assume that stars formed at 1% efficiency from the gas in these shells, though the exact percentage doesn't matter, an increase in the ratio of stellar mass over molecular gas mass in time will show that molecular gas is being destroyed. However, what we instead see is as bubbles get bigger, as indicated by the size of the markers on the figure, and as they get older, indicated by the lighter green marker colour, we see that there is too much molecular gas in the shell to explain the stars in the centre. In other words, these bubbles must be sweeping up and collecting molecular gas as they expand. Despite the presence of stellar feedback, the star-forming potential in the nearby molecular gas remains and actually increases. This matches what we see in high-resolution JWST observations, where we saw 31% of large bubbles contained at least one smaller bubble in its shell, confirming that star formation occurs in bubble shells. We also saw similar results in Ashley Barnes' video on the phantom void, which is a 1 kiloparsec size superbubble in NGC 628. Not only can we see there are many small bubbles around the edge of the phantom void, Barnes et al. Showed it has a gradient of stellar populations. He found older populations in the centre of the bubble and younger populations towards the shell. Finally, repeated cycles of star formation in the shell continually driving the bubble are needed to explain how the phantom void is so circular despite its size. Without large expansion speeds, galactic shear would shred this bubble into a long ellipse quickly. Therefore, all these results show that stars continually form in feedback-dominated systems. So, in summary, we find that on 100 parsec scales, molecular superbubbles are powered by supernova explosions, not a continuous injection of energy such as winds, which is the go-to assumption. We should not always use a single wind-like model to study bubble evolution and the energy they inject into the ISM. Finally, we find that molecular superbubbles sweep up additional molecular gas in their shells and continue forming stars there, despite the presence of feedback. This shows that when gas can shield itself, feedback can do little to halt star formation. Thank you for watching. We hope to see you again in the next video.